This chapter, namely chapter 6, is a chapter about sequences and series. And series of functions. Here we're concerned about about notions of convergence of a given sequence of functions. And what we have in mind is to make sense of expressions like this. You must be familiar with expressions like this because you saw them when you analyze these things when you were in Calc 1 and you consider the Taylor polynomial expansions of a differentiable function. If you add from 1 to infinity, this expression here, if it's well defined, and this given function is differentiable, when can we say that, say, f prime of x is equal to the sum from n equals 1 to infinity of n times a sub n x to the n minus 1. Okay, so this expression here may make sense for every x inside an interval, but when can we say then that we can take derivatives term by term, for instance? More generally, we may be given a sequence of functions. For instance, we can be given a sequence of functions gn, of x where n is in n, and we have that f of x or g of x is defined as, or h of x, just use the same letter. H of x is defined as the sum from n equals 1 to infinity of some functions g sub n of x. What can we say about this, say, h, the derivative h, in terms of the derivatives of gn, or the gn's? Can we move the derivative inside? Can we pull the derivative inside of the sum? This is not an obvious thing. Remember that all these things are limiting procedures, and in general, you cannot just if you have two limits, it depends in which order you actually take the limit. Limits are not obviously interchangeable. It doesn't work like that, and it's actually not true. So for instance here, we know that if h were to be defined, so h super n were to be defined as the sum, or h sub n, so not bring any confusions, would be defined as the sum from n equals 1 just up to n of gn. We will be able to say, of course, if the gn's are differentiable, if the gn's are differentiable, we can say then that the derivative, the h is differentiable, and that the derivative is just the sum of the derivatives of the gn's. This is just the linearity of the derivative. This is in using this notation for summation. This just comes from the fact that if you have f plus g prime, if you have two differentiable functions, then the derivative of the sum is just the sum of the derivatives. So this is something from Calc 1. And of course, if you add multiple functions, the result is the same. So the problem, what is the problem here? What is the problem above? The thing is that this is a problem of convergence. Remember that we can say that this tends to a certain, so this is hn, by the way, it's not h. this, I mean, we talked about this before, and the thing is, how can we be sure that this limit actually exists as n goes to infinity? As n goes to infinity, does this have a limit? I mean, these partial sums. So that's when I mean, that was part of our discussion on series. So to assign a value, this sequence of partial sums need to have a limit. And of course, if that's the case, then since the you can differentiate term by term when you have you can differentiate term by term when you have finitely many terms. And if you can take the limit here to this, I mean, to obtain that, I mean, if that's it, that is your limit, I mean, the series converges, then you will be able to compute the derivative of h. So of the limit of this expression here, by simply taking all the derivatives of the gn's and then adding them all together. But of course, this requires you to also talk about the derivative of this. I mean this function here, which is defined at the sum. So you want, I mean, yes, to n, and you know that this converges to, I mean, you know that this is in the limit, this is equal to, I mean, provided the limit exists, this goes to, by definition, to the infinite series here, sum of the gn's of x. And so the whole point is how to, I mean, we know here at the n level, at the capital N level, we can take derivatives and we can pass the limit. Question, I mean, we can then try to pass the limit, and the question is how to relate this then with the derivative of h. Can we simply do this all the time? Of course not. I mean, this is the whole point of studying notions of convergence, to be able to say when these operations, this process of taking limits make sense. And so now the question is, why? I mean, why is it important that we? I mean, when we take, I mean, because you know the derivative here is a limit. The derivative is gn prime of x is the limit when h approaches 0 of gn of x h minus gn of x, all of that divided by h. And so when I spoke about having to take two limits here, is because we have the limit when n goes to infinity of the sum from n equals 1 to n of g of then the limit when h approaches 0 of gn of x plus h minus gn of x divided by h. This is just g prime, gn prime. And this whole thing, if it exists, is just the sum from n equals 1 up to infinity of gn prime of x. But what do we want? We want to compare this with the infinite sum, infinity of the gn's of x, all of that prime. This is h of x. And this is then the limit when h approaches 0 of the limit now when n goes to infinity of the sum of from n equals 1 to infinity of to n, up to n, sum from n equals 1 to n of gn of x plus h minus gn of x, all of that divided by h. And so you see here what is the difference here? Here we're taking the limit when n goes to infinity first, and then the limit, no, we're taking the limit when h goes to 0 first, and after that we take the limit when n goes to infinity. While for this expression we're taking the limit when n goes to infinity first, and then the limit when h approaches 0. So it's a question about interchanging these limits, and this is not a trivial question. And in general, you should not assume that you can just simply interchange the limits. And for most applications, and for most things that you'll see, there are several theorems that allow you to interchange limits, like in this case, in this particular case of series. But whenever you do that, most of the things you're going to encounter, not only in this course but later on, have to do with some notion of uniform convergence, something that allows you to do things in a way that don't depend on one of on the points where you're taking the limit, or like, this is related, if it rings a bell to you, to the notion of uniform continuity. And it's the same thing here. So there's a notion that there's some delta, some n's here, and so the n here that you need to make sure that this is within some epsilon neighborhood of the derivative doesn't depend actually on n. I'm sorry. Doesn't depend on. Let me go back. So when here, if we can guarantee that h, if h is smaller than a certain quantity epsilon, then this is going to be, this quotient here is going to be within some really small quantity from the derivative of gn at that point, and that's independent of n. Then that's a uniform statement. So the error, you can basically add all the errors, and you're not going to obtain much. And so this whole sum will be what I'm saying is an oversimplification of things, but the idea is that, so if you can make sure that, for example, for every n, the h that you need in order to not make a big error here when computing this quotient, which is not really the derivative, and you can make that somehow uniform in x and in n, then you're done. Then you can interchange the limits here. And so these notions of uniformity appear all the time when you're doing analysis. And now, so to explain what kinds of things that can go wrong, let's try to see an example. Why is it that you cannot just interchange the limit between the quantity depends on quantity depends on two variables. For instance, consider, say, fn of x to be n over n plus, say, x squared. So what is the limit as n goes to infinity of the limit as x goes to infinity of fn of x? This is the limit when n approaches infinity of the limit when x approaches infinity of n over n plus x squared. Here, and this is the key thing. This limit here, if you see, I mean, for this expression, when we're taking the limit when x goes to infinity, n is fixed. It doesn't matter how big it is, but n is fixed. And this actually goes to 0. You see, because n is fixed, and if you take something over x squared plus something that is fixed, then of course it's going to become smaller and smaller, so this limit is 0. And of course the limit when n goes to infinity of 0 is just 0. The thing here to keep in mind, this is important for what's going to come next, is that in order to guarantee that this is going to be very small, I mean that n that you need to, I mean the value of x that you need to pick may change depending on how big n is. And so that's what makes this convergence thing here not uniform. The bigger the n, the bigger the x you have to pick to guarantee that this expression is going to be smaller than a given epsilon. On the other hand, what happens? So that's a problem of not having a sort of a uniform convergence, uniform. That's the problem highlighted here. That you don't have uniform convergence to 0, say, and that's what's gonna allow us to produce this kind of funny thing here when we interchange the limits. We'll see that the notion of uniform convergence in a little while, but this is it. So we have the limit when x approaches infinity of if we instead compute this limit, the limit when x approaches infinity, the limit when n goes to infinity of the same family of functions fn of x, you get the limit when x approaches infinity of the limit when n goes to infinity of n over n plus x squared. Here x is fixed. You see, you can treat this expression here as a polynomial of degree 1 over a polynomial of degree 1. And the coefficients are the same, and the degrees are the same, so the polynomials of degree 1. And so what is this limit? This is actually 1. And so what is the limit of 1 as x approaches infinity? This is just 1. And this is what this is what points out to the kind of problems that we're facing when we're trying to interchange limits. The processes here are not uniform. So the convergence to 1 here is also not uniform. The bigger the x, the bigger the n you have to pick to get really close to 1. I mean, within an epsilon neighborhood of 1. So the n you have to pick depends on x. And here the x you need to pick to make this quotient smaller than epsilon depends on n. And that dependence is what's problematic. And this is what doesn't allow you to say that the convergence is uniform, and ultimately that's what prevents you from interchanging the limits. Of course, here you see you took the limit when n goes to infinity of the limit of when x goes to infinity of fn of x, and you obtain 0. And if you took the limit of when x goes to infinity of the limit of n when n goes to infinity of fn of x, yeah, so the limit of when x goes to infinity of the limit of n of the limit when n goes to infinity of fn x is equal to 1. And these two quantities here are not, of course, the same. I mean, you know that this is 0 is not equal to 1. And so this is what's problematic. And so for that reason, when you have this kind of limits, like trying to interchange derivatives and the limit when x goes to infinity of a partial sum, which is what defines the series, I mean, that kind of thing is what could bring some problems when you're trying to write things like this, to differentiate term by term. Brings us to the beginning of to the opening question here. And now, so with that in mind, we can start introducing some definitions and some concepts that we'll need. Um, uh, and so one thing that you know already have to do with the notion of convergence of a sequence, and so that's what leads us to the definition of pointwise convergence. You know how to talk about, say, a sequence of numbers converting to a sequence of a sequence of numbers converting to a number. Uh, but this is not enough. This notion is not good, and it's not gonna. It's good to know when a sequence of functions converts pointwise to another function. But if it's not uniform, that convergence is not uniform, then this is not going to allow us to perform this operation of interchanging limits. But we need to know what we mean by pointwise convergence. As I said, it has only to do with the sequences numbers converting to a number. It's just that you have a sequence for every single value of x. So definition. Definition 6.2.1 is the following. So just again, you have a family of functions, right? So this is a of functions defined on some A subset of R, and so if you fix a number x here, and you consider the sequence of fn x's, the fn's of x, you just have a sequence of real numbers, and you'll say that you in that sequence may converge or not converge to something, and if you do that for every x, you may you're defining a new function, right? So it's the limit of every at every x it takes on the value of the limit of fnx, so taking as a sequence of numbers, and so we may ask ourselves if the sequence fn I was just writing here to make things explicit, but the sequence of n converges to f, um, f defined on A pointwise if for all x in A, as I said, you can think of it as being a sequence of numbers, fn of x converges to f of x. So here we write, so in this case we write fn converges to f, or the limit goes to infinity of fn of x is equal to f of x. Let's use some example from the book. It's gonna be good later on when we discuss the uniform convergence. Consider fn of x equals x squared plus nx over n. If you fix an x, remember to fix an x, we can take the limit when n goes to infinity of the fn's of x, and here remember, the important thing here is to keep in mind that x is fixed, so you have the limit when n goes to infinity of x squared over n plus nx over n, that gives you this x, and since x is fixed and you're dividing x squared by n, the limit of that, when n goes to infinity, the limit of this quotient here when n goes to infinity is equal to 0. And the second term here doesn't depend on n, and so the limit is just that, so it's x. So given any x, this is the important part, given any x, this limit here is just equal to x. So we can say that then fn of x, or just a sequence of functions. If you, of course, I need to take this the argument here. We're talking about the functions now, not the sequence of numbers. It converges to f of x equals x pointwise. So by this, I mean, why did I make this distinction? Why did I take away the argument here inside the sequence? Because, I mean, that wouldn't be telling us anything. We already computed. I mean, we already computed the limit of n of x for any given x, and we obtain x. So we should be saying that, okay, the statement here is true. The thing is, using the definition, if that happens for every x, which is the case, we just use an arbitrary x here, then if this limit is equal to this function here, which in this case is x, for every x, then we can say the whole sequence of functions, not the sequence of functions evaluated at a given point, converges to the function f of x equals x pointwise. And so that's why I stopped here, and because I wanted to stress the fact that this is the definition. So we're talking about convergence of the whole function, not the convergence of the function of the point, which is something we just did here. I mean, we computed this limit. But if you obtain that this limit of fn of x, these limits are equal to a function at a point x, at the same function f of x. The limits are equal to f of x for every x, then you can say the whole function, or the sequence of functions converge. The sequence of functions converges to f of x, which is the case here. But you see here, I mean, something funny is going to happen here. The convergence here will not be uniform. You see that in order to make this small, I mean the x squared over n small, you're going to have to pick an n that it's going to depend on how big x is. So that dependence on x is yeah, in fact you have to pick larger and larger values the bigger the value of x is in absolute value. So that means that of course, I mean, you cannot fix one n that will work for all x's, and so that makes this pointwise convergence not uniform. We'll see later. And why do we care about this? Because what we want to say is we want to say, for instance, one of the things we want to say is one of the guarantees. If we have a sequence of functions fn of x that are continuous, then the limit is continuous. I mean, if I mean, the sequence of functions converge to a function f, then can the continuity at the limit be inherited from the continuity of the functions? If you just use pointwise convergence, then no. But if you use but if the convergence is uniform, then in fact yes. So that's what we introduce now, uniform convergence. Okay, so this is definition 6.2.3, and as I said, the key point here is that the n that you need to pick is independent of x. So what's the definition of uniform convergence? As I said, it will be the definition of convergence, just that the value of n will not depend on the particular x. Be a sequence of functions find on a subset of R. Just like before, so we have a sequence of functions defined on a subset of the real numbers. We say that Fn converges uniformly to a function f defined on the same set if for every epsilon greater than 0, there exists some capital N in N and now the important part, such that if n is greater than or equal to n, this implies that fn of x minus f of x in absolute value is less than epsilon. And here, in fact, I could have said right at the end of this holds for every x, but so there exists n in n. I rather say it this way: there exists an n in n, such that for all x in A, the quantifier here for all goes after the existence of this n. So this n doesn't depend on x. N being greater than or equal to n implies that f of n, f x minus f of x in absolute value is less than epsilon. So here again, as I said, this quantifier here goes after this one. So the n here cannot depend on x. So no matter what n, what x you put in here, this is going to be smaller than epsilon. I mean, regardless of the value of x. This is not the case for the previous example, because as you can see here, the x squared over n, if your value the value of x is really big, then the n you need to choose is going to be very, very big. So for instance, in the previous case, x squared over n being smaller than epsilon, that's what you want. So that implies that n has to be greater than x squared over epsilon, right? So times epsilon to the minus 1. And here's the problem: x squared. X squared is unbounded, so you can never choose an n that will work for everything. If instead you had a situation where you had to pick, say, n greater than x squared over x squared plus 1 times epsilon to the minus 1, that could be made uniform, because you know that this quantity here is smaller than just epsilon to the minus 1. So if you choose n bigger than epsilon to the minus 1, then that will be greater than this quantity, which is what you're interested in. So if you make this choice, so n just greater than epsilon to minus 1, then n is certainly going to be greater than this, and your conditions are going to be satisfied. And so it just can be made uniform. But this is not the case up here, because x squared ruins everything, because the values of x can be arbitrarily large. Here, no. I mean, x squared, as x goes to infinity, this quotient here is going to 1. And so that's the main thing here, main thing at play. So now we'll discuss some consequences, and then we'll just give so I mean the main applications. So just the cover give the main theorems that you'll need to use in later courses without proof. I mean they just follow the same structure as always. It's just again, it's a good exercise for you to try to do them on your own. But the important thing is that you've already gone from talking about sequences then to series. Now we're talking about sequences that depend on points x, so sequence of functions, and now we can transfer that to infinite sums of sequences of functions. So it's the same thing. It's just transferring everything into the new language, incorporating the new elements, but the basic things are the same. And so that's what we're going to be doing in the next video. So we start with what I just told you, the fact that if you have a sequence of continuous functions converging uniformly to a function f. So if the convergence is uniform, then the limiting function is also continuous. That's our next goal. And then from there on, we'll see. I mean, just again, without proof, we'll just state a bunch of results that are important that involve. I mean, they have to do with our initial discussion here. And of course, if you have questions, you can ask me how to go about them. But the important thing is did you know when you can exchange? I mean, interchange. You know, the derivatives and infinite summation. Okay, so that kind of thing. And then after that, we'll just be left with integration, which is going to be the last part of the course.